Thank you, everyone, and thank you to be coming. My pleasure to be with you today, as always in Cocoon Conference. Who I am, I'm Dr. David Baptiste. I'm French, but I'm working in Germany for a company which is called NV, NORE Netzwerke GmbH. We are a computer security service in Heidelberg, in Germany, and our mantra is to make the world a safer place. I did many conferences, but I especially like to be back in Cocoon many times. And if you want to join us in Germany one day, please feel free to come to Troopers. We would like to share that with you. So, the talk of today is about Windows device drivers and the security of such a component in the operating system. So first, let me introduce you how works the notion of drivers in an operating system. So first we have the distinction between the ring 3 and ring 0, which is for other words called user mode and kernel mode. So two different parts of your operating system and the CPU evaluation. So first you have an application, and the application interface with the kernel linked together with different components called drivers. Application make a request, I don't know, for instance, opening a file. There is a transition from ring 3 to ring 0, which is an assembly instruction called syscall, but it's not so important. And then the kernel takes back the end and makes the operation available. So, for instance, keeping our illustration of the hard drive, the kernel makes a notification to a driver supposed to handle the hard drive, and the drivers make the connection with the hard drive. Of course, you can have intermediate drivers, for instance, drivers responsible to manage the file system, like NTFS, FAT32, and so on. So the goal is to have a subset of drivers so that each of these drivers has a specific operational action in the different layers of the operating system. So the goal is to keep things as simple as possible. Each driver has a specific task dedicated for a specific level of his activity in the operating system. So that's the point, but of course it applies for other devices on the hard drive. You could have the same stuff with different drivers for different devices. And the same way you have a communication with different devices. So to sum up, you have a connection between an application and a device through different drivers. And among this list of drivers, the ones which are very relevant for us today are the manufacturer's device drivers. It's literally drivers provided by provided by hardware vendors. So the software which is literally written by the people who make the device available to you. Why do people write specific drivers for Microsoft, especially for device drivers? Well, to be honest, most of the time there is no real need. Microsoft Windows contains a built-in drivers for many device types. So there is a built-in driver for your device type. You don't need to write your own drivers. Most of the default devices provide you everything you want, but sometimes some device manufacturers want to write their own drivers for instance, adding some extra features to existing drivers, adding extra protocol from the ones that Microsoft provides, and so on. So, well, sometimes also it's to add some vulnerabilities in the system, but that's another story we are going to cover today, of course. We have different kind of drivers in the system. We have bus driver, function driver, filters drivers. To keep things simple, bus drivers are responsible to carrying information through the system between the CPU, the motherboard, and the device by itself. Function drivers are much more something general, like the keyboard, the mouse, the screen display, the video card, and so on. So something which is in between hardware and logical stuff. So this is for specific function in the system. And filter drivers are in-between drivers between bus drivers and function drivers, or top or the other possibility is to be top of function drivers to add extra features on a function driver or on bus drivers, or to filter parameters or changing output parameters from a driver. So this is the usual illustration we have from bus drivers to function drivers, and you can have in between some filter drivers. Okay. Just to make a little technical stuff, make things as simple as possible, we will try to do it. Any drivers has a driver entry, which is the equivalent of the main function in a C program. And the driver entry is composed of many components, and they are mostly used to interface a specific object, which is called the driver object. And in this driver object, we have a lot of information provided by the operating system, and also information that will be used by the operating system to interface with the drivers thereafter. We have also a registry string to have the configuration path of the service from the registry of Windows where the driver is registered. But what is very important for us is 2 points. The driver standards routine and the implementation of a device interface. The device interface for short is the way how we can communicate with the drivers so that any application can directly communicate with the drivers. It's especially useful, for instance, if you are device manufacturers making fancy mouse device with a LED display and blah, blah, blah. And for this kind of device, it's very convenient to have a direct communication with the driver so that you can change the color of the LEDs from your mouse device, same for the keyboards and so on. So you have 2 ways to create a device interface, IO create device, or you have the IO create device secure function. The secure function is, of course, the one we should use today, but in former times, and I mean something before Windows XP, it was only IO create device function available for developers. So that's why it's a bit tricky. So this function, IO create device, secure or not, is used to allow you to make the interface with the rest of the application in the system. And of course, communicating with drivers is a very sensitive topic because the drivers have a lot of privilege in the system. So to help the security and to improve things up, you can define how someone can interface with you in the system. And you can say, for instance, I want only administrator users be able to interface with me, and you can create what we call a security descriptors. I provide one at the bottom, which is literally a copy and paste from Microsoft documentation to allow people to only communicate if you are administrators. Because if you don't provide one, by default, it's any user which can communicate with your drivers. So it's quite open, in fact. So, of course, it's the usual business to use that, but when there is nothing provided, here comes the fun. So let's continue about the journey in driver's world. And in the driver object, we have different elements, and especially what we call the major functions. In fact, this is a place where drivers, especially in the driver's entry, so the main function of the driver, may register what we call a dispatch routine. Routine, that's the name of function for drivers in ring 0. So don't be afraid by the name of routine, it's just a function as any function in C or C++. And we can create specific function reacting to specific event for the drivers. For instance, when someone connects to the drivers, it's ARP mg create. Same for close when the communication is host. For read operation, write operation, and one I like especially, it's the IRP mg device control, so that we can create by ourselves our own command for the drivers. Of course, the names that provide are user-defined names. They can change from driver to driver. How to interface with the drivers? Well, it's not so complex. From user mode, you just create file, read file, write file, if you want coming back to make the read and write operation. But you have also a specific function which is called device IO control. Device IO control takes the handles getting from create file. You can provide an IO control. An IO control, it's a value which gives a specific operation to be performed by the drivers. There are some public IO controls defined by Microsoft, and for documented operation like SSI port, USB, device management, and so on, and some private operation defined by vendors' softwares. Most of the time they are not documented because it's literally something in between the hardware and the drivers. Of course, we can provide input parameters to communicate with the device, and we can have output parameters to retrieve information from the device. The last parameters, just for the sake of completeness, it's just for synchronizing operation so that you can have asynchronous operation, but that's irrelevant for us today. The way we access to the device is very important, especially for input buffer, output buffer, because everything needs to be secure. We literally provide input buffer or output buffer from user mode, from the application, to the driver. So the driver needs to take care of this buffer. The address of the buffer should be in the correct range, everything should be secure, and so on. You have different methods to pass buffer to drivers. I'm going to go fast on it because it's not the heart of the topic, but for short, you have three of them: buffer read, direct, and neither. Buffer read, it's very simple. We take from the operating system, takes the user mode buffer, makes the translation into kernel mode buffer, and everything is secure that way. It's the most efficient way of doing it, but the drawback is it takes time because the operating system makes the conversion every time, so that some drivers do not use it every time. We have some illustration how to see that from reverse engineering, how to retrieve the buffer. And the other method, which is widely used, is a neither buffered method. This method, in fact, directly takes into account the original user space virtual address of buffers, so the user mode buffers, literally, and it's the driver's responsibility to take care of them, to check everything and so on. So it's much more difficult for the driver authors, and then it's very prone to error. Of course, Microsoft provides the tutorials how to do that correctly, but for that, some driver developers should read it. And you know, reading the documentation, it's so much work. So, this is how we can recognize this kind of interface. Usually it's with type 3 input buffer. Type 3, it's type 3 or type third, it's up to you. It's for ring 3, and user mode buffer for output buffer. So user buffer, everything is in the name. And the operation to do that, just to manage this kind of buffer, is very complex. First, you need to be sure that you are in the correct address range of user mode. Then the memory must be aligned. And then you need to check if the input buffer is readable. And you need to check if the output buffer is writable. And you need to do that every time you touch a buffer. The best solution, most of the time, is just to touch the buffer and check the buffer once for all, copy everything in kernel mode memory, and do the operation. But it's more or less buffer method. We have already presented that when the operating system do all the heavy job for you. Surprisingly, this method is still widely used by some drivers, and a lot of drivers have still problems with this kind of communication. Let me show you some historical example of drivers having problems. But first of all, we need to understand why some drivers have problems. Most of the drivers are written in C language, and writing a driver at a professional level is not a mass sport. Why? At least good, reliable, efficient drivers is hard to write because most of the time you need to have a C developer with a high experience and also with a strong knowledge in aware devices and also a strong knowledge in security and also a strong knowledge in operating system and also, well, you get the point. So definitively it's not a mass sport. Of course, some drivers could be written in C++, but it doesn't change a lot the problems. Rust language could be an help, but the main problem with drivers is not, it's literally the language in where they are written. It's more what they provide as features. Let's see that a little bit more. Most of the time, some drivers developers provide some dubious, fancy security or features in the system. Sometimes it can be useful for supporting proprietary protocols, but most of the time they are not so useful drivers. Just as a parenthesis, but in the 2000 year, when I bought a device, for instance a mouse or stuff like that, the device was provided with a little CD-ROM where we were supposed to insert driver for it. And nowadays nobody does that. And if you want to make the experiment at home, take one of these devices from the 2000 years, if it's USB, try to plug it in the system and it will work directly without any drivers. Showing you how useless was this device drivers at that time. But anyway, some device manufacturers like to use some providers to write some fancy drivers. And some of the providers of this hardware manufacturers have a very good power. A superpower, the power of the copy and paste. Let me show you the illustration. Most of the time, the drivers where we have vulnerabilities inside are based on 3 main projects. All Windows DDK sample, WinRing0, and WinIO. This is the 3 main projects, the fabulous 3 well-known projects where everyone make copy and paste to have a lot of vulnerabilities inside. The old DDK samples come from Windows 98, 3.5, and so on. Windows 3.5, so we are literally at the beginning of the 90s. Not so new. If you want to go in a time machine, you can come back and find on internet this old SDK, DDK, software development kit, driver development kit. It's up to you. Feel free to do it. WinRing0 provides you, it's a project which is open source and GitHub, provides you direct access to IO port, PCI, MSR, just to make translation about this technical stuff, direct device communication, or major disclosure of information. Bypassing Ring3, Ring0 protection, so everything about application, driver, security, blah, 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 goes away. ASLR bypass, memory isolation is bypassed, everything like that. Same for WinIO, where you have exactly the same problem, direct device communication, bypassing Ring3, Ring0 protection, and it provides a feature that the other driver doesn't provide. It's mapping of physical memory. So this is a feature coming from 1993, and we are going to show why. Read, write, what, where, so you can directly write or read whatever you want in memory, whatever is in memory, and you have still the problem of bypass. Let me show you an illustration. Coming from Microsoft Windows NT4, the equivalent of Windows client is Windows 98. You see? The codes come from 1993, so it's part of the DDK of that time, and in this DDK you have sample of codes, C code, literally. And these samples is used a lot in different projects. For instance, RT core drivers has been disclosed some vulnerabilities by Ash Firefox, which is a blogger online, and the guy found a lot of issues about these drivers, which has been made by MSI afterburners. Just looking for MSI afterburners online, simple Google search, it was written that MSI afterburners is the world's most recognized, widely used graphic cards overclocking utility, which gives you full control of your graphic cards. Let's see what does it mean from the driver point of view. First of all, the entry point from reverse engineering, but you will see it's very simple. You see IO create device and major function stuff. Literally, it's a copy and paste of one of the 2 projects we mentioned, Ring0 or WinIO. We have create device secure and different ways of doing it. On my left, you can create the driver so that only administrators process can communicate with you. So it's not good from security point of view because the driver provides very bad features for application and bypassing all the security, but at least only for administrators. And on my right, nothing from security point of view. And guess who won? Right. So they make a copy and paste of what was the most useful, no security. We continue? We have a specific function in the middle, which I call WinIO. Let's check in it, what does it mean? First, we have a sort of structures which come from, on the right, the DDK from Windows 98. And in fact, in these structures, they only kept the three last fields. They remove extra information. You know, too much information is too complex to manage. Then, you have this line which comes from this part of the source code, this part comes from this part comes from this part, this part, this part, this part, this part. It's literally copy and paste. That's 1993 source code. The driver is from 2020. We continue. Same function, same superpower of the copy and paste. And we continue. It's every time like that. So it's not hard to make reverse engineering. You just need to follow the original source code. And then, in addition to provide the original source code of the DDK, they provide extra features. In this case, we have literally a right where you want operation. so that you can provide that value in memory, virtual memory in user mode or kernel mode, no matter what, the content of your buffer you want to copy, the size of the buffer, and you write whatever you want. Writing is good, but what could be better is to read memory so that you can know where you are going to write something and where you are going to write something thereafter. So you have a read where you want operations. That's how it works. And because it's very well done, you can choose the granularity of the operation you are going to write. If it's per byte, per double byte, per 4 byte, and so on and so on. Very pleasant stuff. We continue? You have a call to a function which is called map IO space. And inside this function, you have a call to the function of the API, which is called map IO space. This function is documented by Microsoft. The map IO space routines match the given physical address range to non-page system address space. More directly, you provide the address you want from physical memory, and it provides you to the application to you. You know the utility, volatility, and so on used for forensic purpose? Forget about it. Just use MSI drivers. It's literally the same features, but open to everyone. You don't have to be an administrator or stuff like that. MSI registers are specific registers in the CPU, which, for instance, give you the base address of the kernel address. So disclosing any information from them is very sensitive. You have a direct access. And you know where does this code come from? Wing 0, another project. So that they can make copy and paste of some functions. And up, here comes back for read operation, but we have exactly the same stuff for write operation. Always the same story, the superpower of the copy and paste. We have for our input so that we can directly communicate with device. Same problem, same issue. So I propose an update of their description. MSI Afterburner gives you full control of your computer to anyone. That's maybe the most important. And the main problem of this kind of driver is very well known. It's by design. Their market and their business is about to overclock some device which they do not master directly. So of course they need to use some hack or fancy features, blah, 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 to do the stuff. And of course, if the device manufacturers didn't think about it the first time, it's maybe for a good reason. So they cannot change so much this kind of driver because all of their business is based on this kind of drivers. So they can try here and there to correct some stuff so that it's not so accessible to anyone. But it's too less. Too few, too late. Application in real world. At Windows XP time, the name of the game was to write a drivers to make a rootkit. A drivers able to hide any process in the system, able to hide any file in the system, any registry key to the system, and so on. And the goal for researchers and some good friends of mine was just to write very tricky drivers and original method to make rootkit, and we get a ticket for a major conference. It was a very cool time at that time. But with Windows Vista, especially Windows XP 64-bit, drivers must be signed. And if drivers must be signed, it means that we need to give somewhere our name, first name, family name, and so on, and credit card number to sign the driver. So that we cannot continue for hackers to make our own drivers providing rootkit for the rest of the world. That was a very bad news because it was the end of that time. The good news is that before, there was a full list of drivers full of vulnerabilities that just wait to be exploited. So we have still a gold mine of former times that we can still exploit. So it's Christmas again, one more time. So finding vulnerabilities is very interesting for malwares because they find vulnerabilities in the driver, they install the driver on your system if it's not already installed, and the business continue as before. You don't believe me? Okay. Non-usage in the wild. That's the list of drivers And that's the list of malware using that drivers. That's just the beginning of the list. Of course, there are more and more. So we have a long list of drivers associated to malware exploiting that drivers for privilege escalation. But malwares using vulnerable drivers, it's just a subset of vulnerable drivers. If you want a full list of drivers, I would advise you to go on loaddrivers.io. You have a full list of vulnerable drivers. And what is cool, for each driver, you can directly download it, so that you don't waste time to look for it on internet. But there is more. You have also the command line, how to launch it and how to register it. But there is more. You have the type of vulnerability, if it's an elevation of privilege or something else. And you have also some reference to blogs, so that you know where to find how to exploit the drivers. Lesson learned from all of this. What does it mean? First of all, backward compatibility was for the best and for the worst. For the best because your device from the 90s or the 2000 years still works today, and that's for the good. But for the worst, it means that bad design at the time where there was no security in the operating system, not no security, but very few security comparing to today's security, the code still exists and is still exploitable. So that's a big problem. Another big problem is that plenty of device drivers, developers are just ignoring basics about security. Even worse, some of them are just base their business on providing ways to bypass the security. And the drivers are still working and they are still deployed on some system. People are still continuing to use that. Most of the time because we don't know how worse they are. How we could improve things up. From a technical level, Microsoft provides everything you want to enhance the security of drivers. For instance, you have a driver security checklist ensuring you how to make the stuff correctly. It's literally from Microsoft documentation. We assume that sometimes, somewhere, someone will try to use your driver to compromise system security. It's literally written that it could go wrong, and it goes wrong a lot of time. So we may involve to do stuff correctly. The first things to do, from a technical point of view, is to understand what are the inputs of drivers. So how we can interface with the drivers from IRP connection, I/O control, API calls, callback, any other interface specific to specific technology. For instance, a printer, what you receive about to be print, so the file format. Same for antivirus, so that when you scan for specific types of executable file, you should not be vulnerable to parsing issue, and so on and so on. And what can be interesting is to model the security of a driver. So we make some graph of interaction between different components of the drivers, the operating system, device, input, network, and so on. And of course, for instance, under I/O requests, we can zoom inside. So make something much more specific for specific component in the drivers. Operating system, user process, and how we interact each other all together. And Microsoft provides a very good way to do the stuff correctly. It's called Stride. We try to categorize what could go wrong for specific parts of the drivers. Spoofing, tampering, repudiation, information disclosure, denial of service, or elevation of privilege. And for every kind of entry in the driver, we check all of these categories, and we try to understand what could go wrong in each of these categories. And what we do in the end, for instance, when doing vulnerability research on drivers, but it should be done, from my point of view, literally at the beginning of the driver's design and not in the end when the driver is designed, is to make vulnerable point, potential threat, according to the Stride evaluation, and scenarios. When I send this value to the drivers, I've got this output, and so on. So this is what should be done from my point of view. And of course, you can have complex attacks with different codes sent to the drivers, making parallel, so that in this case, I ask the device to read something, and I try in parallel to disconnect the device. And I check if there is a crash somewhere or not. Sometimes yes, sometimes not. From the development level, there is also something to do. Just for drivers evaluation, if I just circle in red what could goes better from development level if it's taken correctly at the correct place. So it's from Microsoft Security Development Life Cycle, SDL. There is a white paper online. I advise you to go there. There is also a book which is very good. And my first point, I would say, is training. During this conference, we make a workshop about device drivers vulnerability assessment, and in this workshop we tried to share our knowledge about device driver security and more generally cyber security, so that from the beginning we can understand where were the problem and how we can try to fix them before they happen. So that's one of the main stuff. At administrative level, of course, is to check all the security of Windows on. Data execution prevention, control forward, and so on and so on. Same for the new security provided by Windows 10 App Container, HVCI, HyperGuard, disabling NTVDM, which is more or less always the case on nowadays computer. SMEP, Supervisor Mode Execution Prevention, which is a nice technology so that normally on the CPU, from user mode, you cannot touch memory in kernel mode. And with this technology, from kernel mode, you cannot touch the memory in user mode. So that if a malicious application passes through your drivers, a buffer incorrectly performed, and you want to try to execute and read it directly from it, you get catched by the CPU, and the security happens. Another stuff which is going to be very powerful in the coming years and provided nowadays by Microsoft is kernel data protection, KDP, based on protect driver section function. Literally, it's, if you are aware of that, of VTL, VTL0, VTL1, is VBS, virtual based security. Microsoft provides you the way so that you can say, my driver, this page of memory should be protected, this page of memory should be protected, so that if someone tries to tamper with my drivers, this is the hypervisor in Windows which takes the on and takes the control of everything like that. At organizational level, I really advise you to use Windows Defender Application Control so that your organization can control which drivers and applications are allowed to run in the system. Microsoft recommended driver block rules about drivers so that when we know that there are some drivers which propose a security issue in the system, we can block them. For instance, for Mimikatz, you have in the list of the Microsoft recommended driver block rules, you have a list of drivers which are blocked by definition or by default. But this list is not so complete. Sometimes there are some drivers which make sense when they are present, and some drivers we all know that they have a security issue, they are not present in the list. So that's not perfect, and I highly encourage you to use that list, but also to complete it. What to do also at organizational level is not to use all fancy device. Okay, the keyboard looks good, but the driver doesn't look good at all. So that's the point. And check carefully which device driver should be installed on your system. Authorize only a subset of certificates from well-known device manufacturers' drivers. And my advice also for you, make them reverse. Make them analyze their drivers to check before you install them if they are secure or not, because they provide so much capabilities for attackers. Default drivers, by the way, ship with Microsoft out of the box, so after a clean install of Windows, they provide for you most of the time what you need for basics as a basic interface with devices. So no need to go further. In case of, if you are interested by, the Federal Office of Information Security in Germany, which is called BSC, has a project which is called Sisyphus, and my company is part of this project, and we make a reverse engineering of Windows for some highly sensitive part of Windows, and it could be interesting if you are interested for going further for this talk to check few of their publications, virtualization-based security, device guards, and driver management, which is about to be published, to explain to you how it works, the security of Windows, and how you should configure your system to have a better security, and also which interface you should request to get logs for what is happening on your system. So I think it's more or less time's up, so it's for me the time to make a conclusion. So first of all, it's not so hard to find vulnerability in drivers because most of the time it's always the same stories, meaning that some drivers, and especially highly vulnerable drivers, are based more or less on one of the 3 fabulous projects. They all make copy and paste from edges, and they literally come from the 90s, not to say the 80s. Then, driver vulnerability are not close to disappear. All legacy deprecated drivers are still usable, and they still will be usable in the future. So that's main topic. We need to learn how to live with that. That's why management and organizational topic is also a concern. SDL, software development lifecycle, is very important in this case, and especially the training side, sharing knowledge, anticipating the issue from the beginning of a new drivers, and the necessity to remediate it at different levels, technical, management, and policy. And on that words, thank you for your attention. My pleasure to have been your guest today.